All right. Now, we're not quite done. There's a little bit more I want to talk about. To finish out today. What shape are all of these orbits? What shape are all of these orbits? What do we call all of these? What shape are all these orbits? Yeah, they're all ellipses, right? They're all ellipses. But here's something that's important. For most of these objects, for everything in the Kuiper belt and everything in the asteroid belt, and for the planets, those ellipses are almost circles, okay? They're almost circles. And so even though the sun is not technically perfectly at the center of those orbits, because these orbits are close to being circles, the sun is basically right at the center, okay? But ellipses don't have to be close to circles. Every once in a while, objects in the Kuiper belt and the Oort cloud get knocked into really stretched out orbits, okay? Either by hitting each other, which is pretty rare, or by being influenced by the gravity of the planets could pull them into another orbit. So every once in a while, you end up with, let me see if I can draw this on here, one of these objects going into an orbit that's shaped like this. There we go. I just drew a really bad orbit. Ignore this little lump right here. That's bad. Whatever. Anyway, if you have a really stretched out orbit like that, is the sun right at the center of that orbit that I drew in red? Is the sun in the center of that red orbit? Yes or no? No, it's not. Remember, the sun is never perfectly at the center of any orbit. It's at one of the foci. It's at a focus. But as we said way back in test 1 material, if an orbit gets more stretched out, each of the focuses, the foci, move towards the outer edge. So if one of these Kuiper belt objects gets knocked into this shape of orbit, then that means the sun is way over near the edge of that orbit. And that means that this object is going to come in close to the sun sometimes. And for a Kuiper belt object, that's a bit of a problem. Why is it that this would be a bit of a problem for a Kuiper belt object? What aspect of these Kuiper belt objects would have a problem coming in close to the sun? Why don't they want to come in close to the sun? Because of a certain type of substance on them. What do they have that asteroids don't have? Yeah, they have that ice in there, so they're going to have a problem with melting if this happens, okay? They're going to have a problem with melting if this happens, right? So if a Kuiper belt object ends up in this shape of orbit, every time it comes around the sun, it's going to melt a little bit. Now, that said, there is something that can help them out. What's probably true about the speed of the object right on this part of the orbit? What's probably true about the speed of the orbit, the speed of the object in this part of the orbit? Is it fast or slow when it's right here? It gets fast because it's close to the sun, according to Kepler's laws, right? So luckily for this object, it's going to be moving slow when it's out here where it's cold, so its ice is going to be fine. When it gets in close where it can start to melt, it's going to be moving fast. So most of the time, it's still going to be out here where it's cold, and it's going to be fine. But it will partially melt when it gets in real close like that. Now, when that happens, some of the material, the melted material, will fall off of the object, and that will make it look different. Does anybody know what this kind of object is when this happens? Let me show you a picture from the book of one of these things melting? Here you go. Here's a picture of a trans-Neptunian object that came in too close to the sun. Does anybody know what this is called? What this kind of thing right here is called? What's this? Close. Meteors are a little bit different. Shooting stars are also a little bit different. This is a comet. C-O-M-E-T. This is called a comet, which is a different thing than a shooting star. Okay? Some of you may have seen a shooting star, right? Some of you may have seen a shooting star zipping across the sky, like making a streak. This is different. Comets are just trans-Neptunian objects that have an orbit that brings them too close to the sun, and so sometimes they melt. So this tail right here, this is melted material from the comet, okay? Now, we need to figure out which way this comet is moving, okay? We need to figure out which way this comet is moving. Now, I can't tell which direction this comet is moving. I don't know which direction it's moving, but you're probably guessing that it's moving this way, right? You're probably guessing that it's moving this way. Now, I don't know which direction this comet's moving, but I do know for a fact it's definitely not moving this way. That's one direction I know it's not moving. It's definitely not going this way, right? It's definitely not going this way. To help explain that, let me draw something else real quick. Here we go. Let's draw this. Get a new sheet of paper. Let's imagine this is the sun. And here's the orbit of the comet coming in. And let's say that the comet's coming through like this. It's going in this way, and that means it's coming around this way, and it's going out when it's down here. Now, when the comet is way away from the sun, it's not going to have any tail. It's not going to have any tail, okay? So, here we go. How do we figure out which way the tail is going to point when it gets made, okay? So when the comet gets in right here, the comet is moving roughly to the right, right? It's moving roughly to the right. But when it gets in close to the sun, some of the ice is going to melt. Now, here's the thing. We haven't talked about the sun yet, but one of the things that the sun has is something called the solar wind. And we'll talk more about that when we talk more about the sun. But the sun is constantly blowing gas outwards in all directions. So the solar wind blows out of the sun in all directions. Let's call that the solar wind. Okay? Now, the solar wind is blowing outward. So check this out. If the sun partially melts this ice and the solar wind blows on that melted ice, which direction would the melted ice go in this picture? Give me a up, down, left, or right. If this thing partially melts and then the solar wind blows on that melted ice, which direction would the melted ice go? Up, down, left, or right? Up, right? It would go up in this area. So it would go like this. Now check this out. Right there, that tail would point up. The comet is moving to the right, but the tail is pointing up, which from the comet's point of view is out the side of the comet, right? It's not pointing back like a rocket exhaust. It's pointing out the side, like it's being blown out of the window. Okay, now, check this out. When the comet gets right here, which way is that tail going to point? When the comet's right here, which direction would the tail point? Up, down, left, or right? Yeah. Right. And you could probably guess what I'm going to get at. If the comet gets right here, the tail's going to point like this. So right here, again, the comet is moving down, but the tail's pointing out its side. Here, the comet is moving to the left, but the tail is pointing out of its side. And so, yeah, the easiest way to explain the direction that the tails point, as some of you have pointed out, is the comet's tail points away from the sun. Okay? This comet's tail is not rocket exhaust. It's not flying along from the sky like a rocket and have like a tail pointing out like poof. That's not what's going on. This is material being blown out of the side of the comet as it whips around the sun. So if we go back to that actual photograph, actually, before I go to the photograph, notice that the comet, for the tail to be pointing back, the comet would have to be flying directly into the sun. And because that's not how the orbit works, that never happens. So I know from the photograph that this comet is not moving that way. It's probably moving that way, like that. It's probably moving in that direction with the tail pointing out the side of the comet. Can we tell where the sun is in this picture? Yeah, we can tell where the sun is. The tail always points away from the sun, so that means the sun must be behind the Earth back here somewhere. Like somewhere down here, the sun is blowing that tail off, okay? Now, one other thing. Have any of you guys ever seen a comet? Have any of you guys ever seen a comet? I'm going to guess probably not, but maybe you have. If you haven't seen a comet, you probably don't know how they move in the sky. And there's a reason. Some of you guys called it a shooting star, and that's one way that I knew you didn't ever see a comet before. Because how many of you guys have seen shooting stars? That's a different question. How many of you have seen shooting stars before? Yeah, you probably have seen a shooting star. And what do those look like? They zip across the sky really fast, right? You just see like a phew, okay? Just a phew across the sky. Now, this is not a shooting star. It doesn't move across the sky like that, okay? If there was a comet tonight, let's say that this comet was coming tonight. If we all went out and looked at it, this right here, this might as well be a video. Comets, when there are comets out, they just sit in place in the sky with their tail just sticking out the side. Like in movies, they go just, but that's not how they work. Movies screw this up. A comet is just going to sit in place with the tail sticking off. You can just sit there and take a bunch of pictures of it over a period of hours, right? Does that mean that it's not moving? No, it's clearly moving, and in fact, it's moving really fast. It's in the fastest part of its orbit. That's not that crazy. What does this tell us about the comet? If it's really, really moving fast, but it doesn't, but if it looks like it's barely moving to us, what does that tell us about the comet? Let's see if you guys can figure that out. If in real life it's moving really fast, I like how you're thinking with that. So someone said maybe it's moving the same speed as us. That could make it look like this. But because we don't share that orbit, it's unlikely that it's going the same speed as us. Let me walk your way up to it. Have you ever seen an airplane way up in the sky? Have you ever seen an airplane way up in the sky? Probably you have, right? Airplanes move, way faster than cars do. Airplanes move way faster than cars do, but they don't look like they're moving that fast. Why? Why does it look like the airplane is moving really slow if it's actually moving really, really fast? There's a simple reason for it. It's the distance involved. It's because the airplane is far away. It's the same thing for the moon. The moon is moving incredibly fast, but it doesn't look like it because the moon is so far away. So let's apply that. If comets are actually moving really fast, but they don't look like it, what can we say about comets? What's true about comets, making them look like they move so slow? Think you guys got it? They're really far away, right? They're really far away. If we look right here, they're in a completely different orbit than us, right? So they're nowhere near. They're much further away than the moon is. So even though they're moving incredibly fast, faster than bullets a lot of the time, we can't see that movement because they're so far away. So comets are not shooting stars.